Okay, so udocker. So my name is Jorge Gomes. I work at LIP, the Portuguese High Energy Physics Laboratory, and also at INCD, the Portuguese National Distributed Computing Infrastructure. So, udocker was born in the Indigo Data Cloud project. The objective at the time was to enable the execution of applications across multiple environments, clouds, HPC environments, farms, and so forth, and to encapsulate applications so that we could run in those environments. And we had lots of different use cases, and we choose to run with containers, namely with Docker containers. And of course, one of the issues was how to run those applications with Docker containers in batch systems. So Docker is not well suited for that purpose, of course, and we had work that we started back in 2013 already on how to do these things. So our idea was not to run Docker at all, but to find a way to run the containers without using privileges, so that we would not bother the system administrators, and so that the software could be installed without privileges and run without privileges, and run as a normal user, so that it would be run within the controls of the batch system and will be properly accounted. So the idea was to empower end users to run applications in containers. So udocker is available in GitHub, source code. We have a master repository and a development repository. You can fetch it directly from the master repository, or you can find one of the releases. The latest one is 1.1.3. And basically, to install, this is a simple way. Just go to the master repository, fetch udocker, which is a Python script, and change mode to make it executable and install. And there is nothing else that is needed. It does not require compilation nor nothing, because everything is shipped together then with udocker. Udocker, upon the install, will fetch everything that is necessary. So these will enable you to pull containers from Docker Hub and other Docker repositories, to import them as well and load. So import is to import a tarball, load is to import the layers of the container. They will be all stored in the user home directory, and then you can extract them and run them with several methods. So udocker is a kind of integration tool that enables then you to run the container with several methods, and we have now 4 methods that we support. So basically, you pull the container, it will fetch the layers, and then you can see the images that you have. You can create a container. Create a container here basically means taking the layers and extracting them, and sorry. It's not working. Okay, no problem. And extracting them one on top of the other, respecting the whitenings of the layered file system, so that you can get them into a directory tree, and then you can see whatever you have in there, and in terms of containers that you had extracted, and you can run them. And it runs Ubuntu on top of CentOS, CentOS on top of Ubuntu, doesn't matter. We have even a kind of emulation of root in the default mode that enables you also to install software. So you can even install packages and do an apt get, or in Fedora to do a yum install or whatever. Of course, there are no privileges involved in here. And you can even map directories. You can map your home directory, and you can define environment variables. You can define your work there, and then these will be translated into the container upon execution. And you can also use all those nice things in Bash to execute multiple commands from the command line or to pass them in scripts. And you can do certain things like cloning the containers. Like you have a container that you have already changed, and you can clone it so that it can be kept. You can create a new one so that you can change it and keep the other. You have certain things that are not standard. You can export, of course, the tarball. You can import the tarball into a new image. But you can also do things that are a bit different. You can import it directly as a container. So this is basically similar also to clone. You have a tarball, and then you can import that tarball not as an image, but directly as a container so that you can save space. And you can, of course, use also clone to clone the containers and import them and export them and import them. This is not interoperable with Docker because we are passing a lot of information that is specific to udocker, not only the layers, or not only the tree, but also some information that is specific to udocker. And you can even do this through SSH so that you can replicate the container across machines if you want. These are just examples. And you can use also with the Docker. Of course, you can do a Docker save and then a udocker load, and all these things work. So you have interoperability with between the tools, and you can do save as well, no problem. And remove the containers. So how does this work? Basically, Python is basically udocker is a Python wrapper around several tools. The Python code basically enables you to fetch the to do the pull, to do the import, to do the export, and the manipulation of the images and of the extracted containers into a local repository that usually is in the user home directory but can be in a different location. And then you have a set of that we call execution engines that enable the execution. And then you can select which one to use. So the 4 that we support now is the first method is based on ptrace. The second method is based on shared library interception. And then we have 2 other methods. One is rootless namespaces, and the other one is singularity, basically, which can be with rootless namespaces or with change root, actually, if it is, depending on whatever is the setup in the batch system where we are running. So the images are downloaded with the layers into the home directory. There is a udocker directory that is created with all the layers in there when you do a pull or import. And then basically we just extract them into a location also under the user home directory. Under these directories, .udocker containers, then this is the container ID, and then root, and the root is the whole tree. It looks like this, and then it's easy. You just need to do something like a change root into this location. Of course, we prefer not to do change root because change root is privileged. So you should not use change root for that. So the way that we do with the default mode is use this ptrace scheme that is provided by proot, by a tool called proot, that enables you to intercept the system call libraries. We'll see the details, and then do translation of the path names in the flight as they occur. Another method is runC with rootless, using user namespaces, and we ship also runC and proot within udocker. And another one is a heavily modified fake change root that enables you to intercept library calls and change the path names also in flight. And then finally, if Singularity is available, we do not ship Singularity, but if Singularity is available on the host, we can also exploit Singularity to run from udocker the containers. So how do you change the execution mode like this? Udocker setup, then you select the execution mode. And here I'm selecting the F3 mode. I can get back to the default P1 mode. And that's as easy as that. So basically these first two P modes, the first two modes, P1 and P2, based on proot. As I said, what they do is basically the system call interception. How this works depends a bit on the capabilities of the kernel. If you are on CentOS 6, basically ptrace will intercept all system calls. Okay, so if your application is doing a lot of system calls, this can become slow. If your application is compute intensive and does not make that much system calls, which is often the case, then it's perfectly fine. If you are on a system, on a kernel that supports seccomp filtering, we can use seccomp filtering to intercept just the system calls that do path name manipulations. And then only open, let's say, and other change directory and whatever, those system calls are intercepted, and then the path names change in flight. For the runC, we just use the plain runC, and we just produce an open containers specification so that we can run the udocker container with runC. For the fake change root, which is the fastest one, we do here a lot of changes into fake change root and around fake change root, because fake change root is a system that is something that was conceived for the debootstrap, basically to build packages on Debian systems. And this enables you basically to run, for instance, Ubuntu 14 on Ubuntu 14, but not Fedora on top of Ubuntu 14 for several reasons. Because basically what we are doing here is shared library interception, and as you probably know, the executables have a health header, and the health header has encoded the loader, so it would fetch the loader from the host and not the loader from the container. That's one of the limitations. The health headers also have path names to search for the shared libraries, and they could point frequently to the host. And they also have eventually the libraries encoded, the path name for the libraries themselves encoded with a full path name sometimes, and then would also point to the host. So we had to make some developments to overcome these things. This is not much relevant. But basically using the first mode, F1, basically what we do is that we invoke first the loader as the first argument, because the loader can be invoked in the command line, and just you pass the executable that we want to run with the arguments after that. So we just shift the arguments, and this enables us to use the loader from within the container. And basically, we force the load of the libraries by defining the LD library path, so that we fetch the libraries from the container. And basically, that's the simple thing to try to run. Then we can go further with the mode F2. And in mode F2, we actually disable in the loader the hard-coded path names, so that it does not use the hard-coded path names that are in the loader, and always uses the LD library path, so that we make sure that it is loading from the LD library path. And the most sophisticated one, let's say, is the F3 and F4 modes. In F3, we actually change the health headers. It takes more time because we need to go through all the libraries and executables in the container, and we change the health headers, and we make sure that it always loads from the container. And then we don't need to pass the loader as first argument, because it will always load the loader from the container. In the last mode, which is F4, basically what we add is some modes to do this in a dynamic way, so that if you compile something from within the container, or if you add packages to the container or so, they will also be changed. Okay, so it does the changes to the health headers of the executables and libraries on the flight. If they are needed, it will perform those changes. So some examples of running. This is, for instance, running OpenQCD. OpenQCD is a lattice QCD, very known implementation for simulations. And this is an MPI application, and we did, for instance, tests in several locations, in SESGA, in a supercomputing center a supercomputing center in Spain, in Galicia. Also in another supercomputer in Altamira, in Santander, at IFCA in Santander. And we ran OpenQCD with up to 250 CPU cores. And actually, when we, in some circumstances, for instance, we could even get a slightly better performance by running with udocker. Why? Because the container was compiled with CentOS 7. Everything in the container was in CentOS 7, and the supercomputer was CentOS 6. So we got some advantages from running with the libraries from CentOS 7 that were newer. And it scales pretty well, as you can see. It's basically the same as running natively. You can see running natively, and you can see running with udocker. And this is another example, DishViz. This is an application that probably was already mentioned today. And we can see running with in the host, and then running with Docker, and then running with udocker. And you see the error bars, and this is all pretty similar. We get some better performance when we are running the container with Ubuntu 16, because the host machine was CentOS 7, and it seems that with Ubuntu it was slightly faster, a few percent faster. And actually this was running with NVIDIA GPUs, with OpenCL. And this is another example that shows that the default mode sometimes is not the best choice. Here we have a lot of overheads in running Romax with the default mode of udocker, and this is using the F modes of udocker, which use fake change root, the modified fake change root. And here you can see that the performance is basically the same or better than Docker, and close to the physical machine. So what we are working in improving the GPU integration. We have already that improved, and we are improving it a bit further. We want to improve the support for running MPI. This is not really a problem with MPI. It's more usually related with sockets, and some problems with the paths to get to the sockets that in Linux are 107. Characters in length, which is not very nice. And when you have containers that are in the home directory of the users, and if you are creating sockets that end up there, that sometimes creates a lot of problems. And this is frequently a problem that people face and don't understand, that the thing does not work, and this is just because of the socket locations. There are some ways of overcoming this, and we are trying to make this more transparent. So better translation of volumes in the F3 modes. This is implemented, but it will be released in the next release. Support for installation with pip. Some command line interface enhancements. We plan to porting it to Python 3, and also to improve the root emulation both in the P and the F modes. And that's basically it.